Good afternoon, everyone. Today we are going to discuss about the binary search trees. So before going to discuss about binary search tree, we see about the binary tree. So what's a binary tree? It should have consist of two properties. In that one, first property is each node can have up to two successor nodes. See here, for example, each node can have up to two successor nodes. So A consisting of two childs, B and C. So B consisting of two childs, D and E, maximum. I mean, we can have 0, 1 or 2. Up to 2 nodes we can have. See here, C consisting of one node as a child. So like this, that is the first property of binary tree. And then the second one is there should be a unique path should be existence from the root node to every other node. For example, if you consider this tree, so here it is not a valid binary tree because we can reach this D node by using from A to D or by using one more path called A to B, B to D. So here it exists in two paths. So it is not a unique path to reach the D. So if it exists like that, a unique path from root node to every other node, then we call it as like a binary tree. And some of the terminologies are the successor nodes of a node are called its children. See here, for E, this is the successor node, the next one. So A and F are the children for E. B and G are the children for A. BAG is children for E. So DI is the children for F. And CH is the children for B. So all these C, H, B, G, J, A, F, D, I all will be the children of the E. So the successor nodes of a node are called its children. And the predecessor nodes of a node is called its parents. So predecessor, previous one. So for A, before A, we have E node. So it is the predecessor node. So for A, E is the parent. The predecessor node is called as its parent. So for A, E is a parent. For F also, previously we have a node E. So F also the parent is E. So likewise for B, A is the parent. For G also, A is the parent. And for D, F is the parent. For I, F is the parent. So likewise. And the beginning node is called as the root node. So and it has no parent. It is itself is the first node in the tree. So that is called root node. So see here in this example, E is the root node. So this E is the root node. For this one, there is no previous node, that is no predecessor node. So it is no parent. It is consisting of no parent. So it is called as the root node. The next one, a node without children is called a leaf node. So for C, there is no successor nodes. So there is no children. So this is called leaf node. Even for H, children means so it's consisting of the successor nodes. But if there is no successor node, then we call it as a leaf node. For H is also there is a no successor node. So that's why H is a child node or leaf node. Sorry, leaf node. J is also a leaf node. And I, D, all this will be the leaf nodes. And nodes are organized in levels. In trees, nodes are organized in the levels. See here, level 0, level 1, level 2, level 3 and so on. Like this, in levels we organize the nodes. And level of a node can be taken as the number of edges in the path from root to that node. Level. So for B, it's a level 1 because it has one edge from root. D is in level 2 because it consisting of two edges from root node. From A to B, one edge and B to D, one edge. So it is two level. For G node, from root node to G, it is consisting of three edges. That is A to B is one edge and B to D is one edge and D to G is an edge. So it is consisting of three edges. So it is level 3. So likewise, level of a node can be identified. And full tree. is nothing but every node has exactly two children and all the leaves are on the same level. Each and every node should consisting of exactly two children and all the leaves are on the same level. Whether it is a full tree or not, it is not a full tree because see here E is not consisting of any child. Every node has exactly two children. A is consisting of two children, B and C. B is consisting of two children, D and D. So all these are obeying the property. Even C is not obeying the property. See here, for C we have only one children, that is F. Every node should consist of two children exactly, and all the leaves are on the same level. All leaves are on the same level. No, E is a leaf node here because it has no children. So this is not in the same level. It is in the level 2 and remaining leaves are in the level 3. So it's not a full tree. So how to search a binary tree? So we'll start with the root node and search the tree level by level. See, first we'll search the element in level 0, then we'll search the element in level 1, and then in level 2, and then level 3 likewise we'll search until unless you find the element you are searching for your reach leaf. So for what element we are searching? Up to the leaf we'll search the value. So is this better the searching a linked list? No. So to overcome this one, we'll using the best search trees, that is binary search trees. So what is the binary search tree? So a binary search tree is uh, a tree, binary search tree, if each node n of t satisfies the following properties. So what are the properties? The major property is the value stored at a node is greater than the value stored at its left child and less than the value stored at its right child. This is the first and major property. It has to satisfy. So that is nothing but whatever the node we are considering, for that node, all the greater values has to be stored in the left subtree and the values that are less than the node we are considering should be stored on the right hand side. So what are the different operations which we are generally encountered to manipulate this binary search tree data structures are: first one is searching the data, inserting the data, deleting the data, and traversing the tree. These are the major operations we'll perform with the binary search tree. So what are the major operations? Searching, inserting, deleting, and traversing. We'll see with an example how to construct a binary search tree and how to insert, how to delete, and how to search the elements in a given binary search tree. Suppose if we have elements like 65, comma 19, comma 15, comma 28, comma 25, comma 74, comma 57, comma 69, and 88, comma 81. So these are the elements. By using these elements, we have to build a binary search tree. First, we'll start with a value that is 65. So till now, we didn't have any So till now we didn't have any tree. We did not formed any tree. So we'll consider the first element itself as the root node. So that is 65. So this is your first element. Now the second element, consider the second element, that is 19. So now we have to insert 19. So while inserting any element, we have to remember the property of the binary search tree, that is the value at n is greater than the every value in the left subtree of n, and it is less than every value in the right subtree. So now so nine all the elements in the left hand side left subtree should be less than the root node, and all the elements that are the greater the values that are than the root node should present on the right hand side. So now based upon that property, we have to insert the next element, that is next element 19. So inserting of 19, so that is nothing but, so now compare that 19 with the parent value. So 60, compare 19 with the 65. So 19 is less than 65. So it has to be inserted the left hand side. So that is 19. And then the next element is 15, we have to insert. So that is, we have to insert now 15. So compare it with first root node, that is with 65, it is less than. So we have to insert on the left hand side. And next we have one more node called 19, the next node. Value of node is 19. So now compare 15 with this 19. So it is less than the 19. So we have to insert the 15 onto the left hand side of the 19. The left hand side of this one. So that is 15. So likewise, we have to insert all the values into the tree. So the next one is 28. So compare 28 with the first node, that is 65. It is less than the 65, so it has to insert left hand side. Now compare the 28 with the next node, that is with the 19. So it is greater than the 19. So we have to insert on the right hand side because it is greater than the root node. So that is 28. The next element is 25. Compare 25 with the 65. It is less than, so left side. Compare it with the 19. It is greater than, so insert right side. Compare with the 28, less than, so left hand side of the 28. The right hand side, left hand side of the 28 is 25. And then 57. Next element is 57. So compare it with 65. So it is less than, so left hand side. Compare it with the 19. So it is greater than, right hand side of the 19. Compare it with the 28. It is greater than, so right hand side of 28. That is 57. Likewise, we have to insert all the elements. Next one is the 74. So it is greater than, so right hand side of the 65. So that is 74. The next one is 57. Completed 57. Next one is 69. Compare with the 65, it is greater than, so right hand side. Compare with the 74, it is less than, so left hand side. side 69, and then next one is 88 greater than the 65, so right hand side greater than 74, so right hand side. Is 50, sorry, that is 88, then 81 greater than the 65, so right hand side greater than 74, so right hand side. So when compared with the 88, it is less than, so on the left hand side of the 88. So this is how we construct the binary search tree. We will insert the elements into the binary search tree. The next operation is searching a binary search tree. So searching data in the binary search tree is much faster than the searching data in arrays or linked lists. When compared with the remaining arrays and linked lists, searching is very faster in the binary search trees. So how we'll perform the search operations? We'll start with the root node. Then if item is less than the value in the root node, we proceed to its left child. So all the lesser values we are storing in the left hand side of the root node. So if the value that is we are searching is less than the root node, then we'll search in the left hand side of the binary search tree. If the item is greater than the value in the root node, so then we'll proceed to its right hand side. So we'll continue in the right child. So this process will be continued till the item is not found or we reach the dead end. So this is how we'll perform the search operations. See here in the previous example itself, if we want search, if we want search some element called suppose 57. So we'll compare 57 with 65. So it is less than. So we'll consider only left hand side subtree and we'll leave the right subtree. So now again, so it is not equal. So we'll proceed the procedure. So now we'll compare it with the next node, that is with the 19. So it is greater than the 19. So we have to search in the right side of the 19, right right subtree of the 19. So and again we have 28. So it is greater than the 28. So again right hand side of the 28. So that is 57. So here we found the element. So this is successful search. Likewise, we'll perform the search operations. And then the next will be the deletion operations. In the deletion operations, we have three cases. That is, whatever the node we are deleting, so that itself is a leaf node. So that is one case. Or else, if the node is consisting of one child, that is one case. Or else, if the node is consisting of the two childs. If node is consisting leaf node which we want to delete, then simply we delete that node and no problems causes with that one. See here for example 88 consisting of these are all the child nodes, that is 25, 57, 81. These are not consisting any children, so these are called as the leaf nodes. So if it is in the case of leaf node, if you want delete 25, simply we can delete this node. So no need to balance or no need to modify the tree. So nothing will happen to the tree, no imbalance will be happen to the tree. So that is deletion of leaf node. If you want delete a node that is consisting of single child. For example, consider 88. So if you want delete 88, that is it is consisting of one child called 81. So in this case, we'll delete this node and whatever child consists, we make that child value as this node. We make that node as the parent node. So that is the single child node if it is. If it is consisting of the two child nodes, like if you want delete an item called in a value or node called 19, it is consisting of two childs 15 and 28. So now to remove this node, first we'll remove the node and then we have to replace this node with a value of a maximum value in the left hand side subtree or minimum value on the right hand side subtree. So either of which one value we can replace. If you consider this one, here the left hand side the maximum value is 15 only one node we are having, and right if you consider right hand side we have maximum value 57. So we can replace it with 15 or 15 or 57. So this is about the deletion operation, search operation and insert operation in the binary search tree. Thank you everyone.